a.m., New York Harbor. David and I are on a tugboat heading down the Hudson River. We're on our way to help bring a big passenger ship into port. That's Joe McDonald, the captain of the Miriam Moran. Miriam Moran is the name of the tugboat. Why do you need tugboats anyway?
Your ship, when it's stopped, you lose your control, your rudder control there, or when it's going very slow. And the tugs act as rudders there to
steer it.
You have your current and your wind that work against the ship there, and this is what you use your tugs for, is to compensate for these forces.
Oh, because those change the direction of the ship, so you...
That's correct. They will
figure those in when you're figuring out how to steer the ship.
That's right.
If it's really windy and the current's strong, you'd probably need 6 tugs to bring in a ship this size. But today's pretty calm, so 2 can do the job. Unless it's going fast, you can't steer a ship like this. But it can't go fast near the dock because it can't really stop. It might crash. So the ship turns off its own power, and the tugboats will have to push it into port. The Queen Elizabeth II, or the QE2 for short, weighs 63,000 tons and is 3 football fields long. She carries 2,000 passengers, has 4 restaurants with 207 waiters, 22 elevators, 2 banks, 1,300 telephones, 2 discos, and 4 swimming pools. We're on the tug at the front, or bow of the ship. Our sister tug, the Margaret Moran, gets into place at the rear, or stern.
The whole principle of docking a ship is where you apply the pressure to the ship. It causes the ship to turn, and going into a pier is coming up. In this case, it would be perpendicular to the berth that it's going into. And as you apply pressure to it, you turn it so that it's parallel to your berth.
The berth is what, the port? Like where?
The berth is a pier that it will be secured to or moored to.
I understand how why you need force to push the ship, but do you need force also to stop the ship?
Yes. Whenever you have an object in motion, it takes an opposite force to stop it, and you want to be able to stop the ship. Otherwise, it would continue into the pier or the dock, wherever it's going.
Destroys the pier.
That's correct.
So the tugboat uses its horsepower to apply an opposite force and stop the ship or push it into place.
That's correct.
The first thing the tugs have to do is turn the ship around so it's headed toward the pier. Once the ship is turned around, the Margaret pushes from behind, and we push from the side. A ship this big is very hard to stop once it gets moving, so you have to move it slowly so you can control it. The whole job takes about 4 hours. Finally, the ship is safely in place, and lines are lowered to secure her position at the dock.
Hiya! You know what this is? It's a lever. A lever is a simple machine. A simple machine is something that helps you move things. This is how a lever works. You take the lever and put it on something it can turn on. Something like this. This is called a fulcrum. You put one end of the lever under the thing you want to move. And it can be something heavy. This thing weighs 50 pounds. You put the fulcrum under the lever. You push down here. And look, you can move the heavy thing. See? But it makes a difference where you put the fulcrum. If you put it here, near the end of the lever, then it gets really hard to push. But if you put it here, near the heavy thing, then it gets really easy to lift the heavy thing up. But the heavy thing doesn't travel very far. That's the whole secret about levers. They make it easier for you to move things, but you're sort of making a trade to make it easier. You're trading effort for distance. That means the easier it is to move the heavy thing, the shorter the distance the heavy thing will move. Scientists call this kind of trade-off mechanical advantage. I call it a big help.
These are members of the Miami, Florida Junior Rowing Club. And that's me, with Dr. Manuel Huerta, a professor of physics at the University of Miami.
Dr. Huerta, why are these boats so long and skinny?
Well, Robin, the first thing the boat has to do is float.
Okay.
Now, for that, you have to, what we call, displace a certain amount of water. The part of the boat that sits under the waterline pushes aside enough water so that the weight of that water has to be equal to the weight of the boat and the people in it.
Oh.
Now, you can do that a lot of different ways. You can make it short and fat or long and skinny, but you're going for speed. These are race boats.
So if you're going for speed, does it make a difference if it's long and skinny?
It makes a lot of difference. It's not easy to move something that's shaped like a wall through water. It makes a lot of resistance, a lot of friction. If you take a short boat, like a toy boat, and you drag it through the water very fast, what happens?
It makes a lot of bumps.
It just jumps all over the place, makes spray, makes little waves. All that is wasted energy. A long boat doesn't do that. So it's a compromise, and longer is better. You notice how smooth it is.
Yeah.
That will cut down just the rubbing friction against the water.
Now I have one more question to ask you. Why are they facing backwards when they want to go forwards? That doesn't make any sense.
Well, that makes it better for the athletes to put their whole body into it. As you know, you can face one way and move the other. Like if I push you, I'm facing you, but if I push you that way, which way am I going to move? I'm going to move this way. Well, they're pushing against the water with their oars, just like I'm pushing you, and the boat is going the other way.
Facing backwards enables them physically to go
physically to push harder.
It really is an attractive sport. Everybody moving at the same time and everything.
It's beautiful, the rhythm.
Yeah.
The rhythm from a helicopter, it looks terrific.
It's nice, even when you see the guys move back and forth all together.
Right.
That's nice. But let me ask you something. Why are these shoes stuck down?
Well, you know, when they push themselves back in the stroke, they're pushing against that board with their legs. But then they have to come back up, so they pull themselves up with their legs, and if it wasn't attached, their feet would come up.
Right. Now, is everything in the boat specifically designed to help the speed of the boat?
The whole boat is about 150 pounds, believe it or not. Everything is lightweight. The material is very thin, the Kevlar, these graphite washboards, the ribs. Everything is made for lightweight, strength, and speed. including right down to the tips of the oars. Let me show you. You know, the tips of the oars are curved like that so that when the rower puts the oar into the water, it offers a lot of resistance and it almost gets stuck there in the water. And it doesn't move. It's at rest relative to the water, and it's the boat that moves this way.
Oh, so when they pick it up, they push it in, it stays still, and the boat moves,
And the boat moves
that
back.
way. Ah.
If the oar moves, it's bad for the race. For example, if they miss some of the water and the oar
It
does
skips.
a little bit of this and skips, they lose the race.
Now, that's why he kept telling them to get the blue part all the way
That's
in the
right,
water.
to make sure that it's
All the way submerged.
good and stuck in the water.
Oh, because then it goes faster and they don't waste any energy.
That's right. All the little whirlpools and splashes that take place at the oar tip are wasted energy.
Now, what is this for, this silver piece?
Well, this is called the outrigger. And you know, the oar, there's a couple of ways you can think about it, but you can think of it as a lever, where this point is the fixed point. Now,
When you
this
say
is,
fixed point, you mean the stationary point.
it's a stationary
Okay,
point.
and this moves and this moves.
Right. Now, this thing is out here because imagine if the oar lock were very close
It'd
right
be
on the board.
uncomfortable.
What a short oar you would have to
Yeah,
work with.
right.
Nobody could pull that. The force would have to be too great.
Right.
So you put it out so as to give you a reasonable, what is called lever arm to work with. But the
Right.
idea, however, is that this arm, the one to the oar tip, is a lot longer than this one because when the man pushes here, a small arc where he sits
And
will
a
give
large
you
one.
a much bigger arc there. So a
Because
little
of the
bit of
lift.
motion here is a lot of motion out there. So a little bit of motion here, the boat moves a long distance.
This is really complicated. I thought all you did was get in the boat and row. But the feet are nailed down and the seats move back and forth and there's a lever and it's just complicated.
Well, you know, there are levers all over the place. For example, in your arm, there is a couple of different ways to understand it as a lever. Why don't we take you to see Joy Jarrett at the University of Miami,
Oh, okay.
who is a friend of mine, and she can explain to you how all these seemingly simple things that you do every day are actually involve levers and all sorts of mechanical components.
Okay.
So I'm off to see Joy Jarrett. She's a physical therapist at the University of Miami.
Okay, sure. I can better explain to you the principle of levers on Oscar.
On
Why don't you
Oscar?
come? Yeah.
Okay, let's
come over
see
here and meet
Oscar.
Oscar. And Oscar's our skeleton.
Oh, hello, Oscar.
Yes, this is Oscar, and I'm going to show you how the lever works. The lever system works on Oscar. Oscar is able to flex and extend, and he's doing this motion around the fulcrum, which is the axis of rotation.
That means the elbow stays still and the other part moves.
Exactly. Now, when Oscar flexes or pulls his arm up, this is called flexion, and the muscle that's working is the agonist or the prime movers.
Is that the bicep?
Exactly. Now, as he extends his arm, the back muscles of the triceps are working, and then you have the
Relaxing
biceps
the front.
relaxing. Exactly.
So do we have any other levers in our body?
Sure, we have levers around each joint.
So right here?
The shoulder joint is
And,
a lever.
and my wrist too?
The wrist, exactly.
And you have levers in your legs then?
Oh, of course. The fulcrum in the lower extremity right here is the knee.
How many muscles do we have in the body?
Oh, we have about 650 muscles.
Oh, 650?
Yeah, that's,
Wow, that's a lot.
Yeah, that's
but
a
when
lot.
they row, they use the leg muscles the most.
yeah, because those are the powerful muscles. Those are the muscles that are able to generate a lot of force.
That means then that they can go faster with the leg muscles
Exactly.
than with the arm muscles.
Of course. Why don't we go over to the rowing machine, and I think you'd better be able to understand the whole concept.
I can get on the machine?
Sure you can.
Okay.
Let's go.
Okay, now what do I do? Just row?
Yeah, but before you row, I want to show you something on the oscilloscopes. If you look over to your right, the first one is attached to your arms, and the one behind is attached to your legs. Now, what you're going to see on the oscilloscopes is actually your muscle fibers firing.
Now, how will you be able to tell that the muscle fibers in the leg fire more than the arms?
Okay, the wave on the back oscilloscope should be higher and faster. On the arms, the waveform will be slow and the amplitude or the peaks will be shorter.
Okay, I'm ready.
Okay. Now look at the one behind.
Yeah, that was really going fast.
Right.
You very seldom see it at all on the arms.
Yeah, it's smaller. Those legs are really working hard. See?
Yeah. Wow. Now I know that when I row, My legs are really doing a lot more work than my arms.
They are.
And not only that, other things are taking place. The legs are levers, the arms are levers, the oars are levers, and even other parts like my torso.
Exactly. When you flex and extend with your body, you've created a lever.
Not only that, I am the person who's generating the force to make the boat move.
Exactly.
It's
You're
my
right.
muscle fibers that are firing and making the boat go.
Correct.
I want to learn how to do it. Now that I know the principles, it'll be easier for me when I get out there.
Sure. Good luck.
I appreciate you teaching me
You're
that.
welcome.
That was nice.
Watch it move, it's in motion, motion. Watch it move, it's in motion. It takes force to start, stop, bounce, smash, turn, throw, kick, squeeze. Speed up, slow down. It takes force to jump, run, push, pull, open, close, fall down. Watch it move, it's in motion, motion. Watch it move, it's in motion, motion.
This is the United States. The next film takes place here, in France. This is an obelisk. It's a large carved stone weighing more than 19 tons. In the summer of 1985, in the small French village of Plabennec, the townspeople performed an experiment. Could they move an obelisk and set it upright the same way it was done 5,000 years ago? Not using machinery, just human power. Our friend Dominique was there to help. First, ropes were tied around the stone. The ropes were heavy and strong, and it was important to tie the right kind of knots. 2 wooden tracks were placed side by side underneath the stone, leading to a big hole. It's easier to pull the obelisk on wood than on the ground because the wood is smoother and there's less friction. Even so, it took 200 people pulling on the ropes to slide the 19-ton obelisk across to the hole. Gravity pulled the stone into the hole. Then came the hard part. To get the obelisk upright, they had to lift it. Lifting is harder than sliding. They built a wooden frame. The ropes crossed over the top of the frame, and as the people pulled, the force of their pulling was redirected so the ropes lifted the obelisk. It took 400 people to lift it up. It's up! Soon they'll take away the ropes and fill in the hole. Dominique said she thought she knew why they only did it once every 5,000 years. Lifting a 19-ton stone is hard work.
Here we are, back at the QE2. This time, we're going to help bring the ship back out into the river. Another tug, the Dorothy Moran, is at the stern, while we move into position at the bow. First, a rope is dropped down to us from the ship. It's attached to a bigger rope, which is pulled back up. That's attached to an even bigger rope. We watched from the bridge with engineer Nick Svensson.
Why such a sophisticated design with the rope?
Well, there's a reason for it, because they're making a figure 8, and then as the pressure comes on it, and like the backing off or the towing, it closes in and tightens up itself. So there'll be even pressure on the whole lines, they won't burst. And that's the reason why they use it this way.
So you tie it so the force of the moving boat helps to tighten the knot.
Right, and it tightens it even this way from the bottom up. You know, the more the pressure it is, the tighter they get, and it'll be stronger.
That's really smart.
Yeah, but they long time, you know, experience, and they learn over many years.
And if the rope breaks, it could be very dangerous.
Oh yeah, and when the break is from friction or heat, and all the end get like razor blade, and it can really make a mess.
Wow, you mean it would just, what would happen?
Well, they breaks, and they're like a rubber band, you know, because it's synthetic, and they come back like a slingshot.
It's synthetic?
Yes, either nylon or Dacron or combination of the two.
That rope will stretch?
30%.
Like a rubber band?
Yeah, and then come right back to its original shape.
The captain signals that it's time to leave. And the ship is released from the dock. The two tugs use their power, 3,500 horsepower each, to pull the QE2 away from the dock. Once we've pulled the ship away from the dock, it's safe for her to move under her own power. But she still can't steer because she's not moving fast enough. So one of us is still needed to turn her around to face out of the harbor toward the Atlantic Ocean. And finally, the QE2 is off, heading to England. 321 Contact is a production of the Children's Television Workshop and FR3.